This lesson is on surface integrals, but let's first remind ourselves of how to determine surface area if I have a surface defined by some function z equals f of xy. Now, let's remember how this works. What do we have here? At a point x naught, y naught, the partial derivative with respect to x is essentially equal to, approximately equal to the change in z divided by the change in x. And of course, when we take the partial derivative with respect to x, y is not changing. So if we extend from this, then solving for change in z, we would say f sub x times change in x equals change in z. And then this leads us to our vector u that is going to be in the tangent plane. So we know f sub x is going to help define us a vector that is going to sit in the tangent plane. Change in x is in the first slot. There is no change in y. And we've just said the change in z is going to be f sub x times the change in x. So this vector will live in the tangent plane, as will f sub y, using the same kind of argument. Change in z over change in y holding x constant. So f sub y times change in y will equal change in z in that direction, which will then tell me that a second vector in that tangent plane would be what? No change in x this time. Change in y is here, and then the change in z is going to be f sub y times the change in y. So here is the xy plane. There is our region of integration. Here's our surface, z equals f of xy, and we are going to take the image of our region up in that surface. Now I have my point here, which is x naught, y naught. Then it gets mapped up to a point up there, which is f of x naught, y naught. Now in the x direction, here will be my vector u, and there's my vector v. So we see that the area of that parallelogram is going to be the magnitude of that cross product of u with v. So that's going to be the parallelogram that this point is going to get mapped to. And each point is going to be mapped to a small parallelogram. Now, keeping in mind, of course, right, we have change in x, change in y here. And then as we move that up, it'll be approximately a plane, given the fact that change in x and change in y are very small. So what do I know? I know the area of that parallelogram is going to equal the magnitude of u cross v. So let's do our analysis on that to see what that magnitude is going to be. So here is u cross v written as a determinant and expanding accordingly in the I direction, 0 minus f sub x, change in x, change in y, minus in the j component, of course, f sub y, change in x, change in y, plus in the k direction, change in x, change in y minus 0. So there is our u cross v. So let's factor out the delta x, delta y, and we see this. So then what is the magnitude of u cross v? Remember, the area of that little parallelogram is the magnitude of u cross v. And this is what we have. And for the sake of argument, let's assume that change in x and change in y are positive. If that's the case, I can relax the absolute values and say that the magnitude of u cross v is going to be the square root of f sub x squared plus f sub y squared plus 1 multiplied by change in x, change in y, which is in essence the same argument done earlier in the semester when developing a formula for the surface area. So that was the area of that one little parallelogram. So fine, the area of that little parallelogram in red that is mapped up from the little rectangle here in black is going to simply be the square root of f sub x squared plus f sub y squared plus 1 dy dx or dx dy. Of course, we're still in the deltas, so we'll go ahead and do it that way. Now, what is the total area going to be? The total area will be the sum of that is the sum of all those, because all of these points will get assigned some kind of a parallelogram. So the total area is the sum of those things over the entire region. F sub x squared plus f sub y squared plus 1, change in x, change in y. And then what do we typically do here? We're going to shrink those change in x, change in y to 0. And then we'll get our total area will be the double integral over the region R of the square root of f sub x squared plus f sub y squared plus 1 dx dy. And this is going to be the surface area. So I'm going to go ahead and change that to an S because that's the direction that we're going to want to look at it. Yes, that is that area of the portion of the surface that is above that region R. So that's going to be the first part of our discussion on surface integrals. We imagine the following surface, and we've discussed how to find the surface area if we can express z as a function of x and y. But now we want to decide what the mass of that surface is going to be. So we assume it's very thin and the density is changing for the sake of interest. But even if it's not changing, the mass of that little parallelogram will be the surface area of that parallelogram times its density. So how many cubic feet times the pounds per cubic feet, that will give us the mass of that little parallelogram. So the total mass then would be the sum of all those things. So the sum of the density times the area. So let's say the density function is g of x, g of xy. And then the area we've looked at previously, what is that going to give us? So here's our formula using g as our density function, and our surface up here is z equals f of xy. That pen doesn't want to work. Z equals f of xy is our surface here. So that's our formula for the total mass of this. I guess I should have said change in x, change in y there, but of course we're going to shrink that to 0. So we'll say that the total mass will be the double integral over the region R of that of g of xy times the square root of f sub x squared plus f sub y squared plus 1 dy dx. That's what that is, as long as, again, our function, our surface is defined by z as some function of x and y. So let's take a look at an example. So notice this is a double integral, as we have done before, a double integral over some region in R2 that is going to be defined this way. Now, let's take a look at an example of a surface integral written in a slightly different way. So this is the double integral over sigma of z squared ds. Now, what does that mean? Z squared is the density function. So as z grows, the density increases. And ds tells me we're integrating over a surface. Now, this is a portion of this cone. So what do I have? If we look at this cone, it's going to look something like this. But I only want the portion of the cone between z equals 1 and z equals 2. So I'm looking at this portion of the cone, which I'll highlight here in red. So I'm looking for the mass of that cone as I'm moving up. And again, as z increases, the density increases, so it will be heavier up towards the top per square inch than it is on the bottom. So that is, in essence, what this is asking. So let's go ahead and do our analysis. What do we need? We want to go ahead and convert this into an integral of a standard variety integrated over R, some portion of 2 space. So as we said previously, the total mass will be the double integral over some region R that we need to think about of our density function, which I'm going to call g of xy. Notice there's no z there. And then we have the square root of our f sub x squared plus f sub y squared plus 1 dy dx. Now, how are we going to do this? So we've got to figure out what is R. We've got to figure out what is g of xy. We've got to figure out what this thing is. And again, our surface is defined by z equals f of xy. So how can we do this? Well, we see our density function, g of xy, currently is equal to z squared. So recognize that is not a function of x and y. But what I see here is I see z is the square root of x squared plus y squared, which tells me that z squared equals x squared plus y squared. So my density function here is going to be x squared plus y squared. So that's good to know. So where are we at now? Total mass. Again, we have to figure out what our r is going to be, but our z squared, replacing z squared, is going to be with x squared plus y squared. Now, what is our change in s? We've seen that before. That is the square root of f sub x squared plus f sub y squared plus 1 dy dx. So I still need to figure out what f sub x and f sub y are, and I still need to figure out what r is before I can convert this from a surface integral into a standard sort of double integral. Our surface is defined by f of xy. Our surface is that portion of the cone that was defined by z equals the square root of x squared plus y squared. Notice this is written as a function of x and y. I'm going to go ahead and call that f. That is our surface of interest. Our surface is defined by a function of x and y, so I'm going to rename that x. That enables me to use this formula. So I need f sub x and I need f sub y, so let's quickly do that computation. So here's f sub x. You have x squared plus y squared to the 1/2, pull the 1/2 down, x squared plus y squared to the negative 1/2 times the derivative of the inside times 2x. 2x over 2 is x, and the denominator is the square root of x squared plus y squared. And using the similar argument, f sub y is y over the square root of x squared plus y squared. So you'll see I need to have f sub x squared plus f sub y squared plus 1. So f sub x squared is x squared over x squared plus y squared. F sub y squared is y squared over x squared plus y squared. So now let's take a look at f sub x squared plus f sub y squared plus 1. What will that be? So we get here, but notice we have a common denominator here of x squared plus y squared. And I have x squared plus y squared over x squared plus y squared plus 1, which of course just equals 2. So this thing up top, f sub x squared plus f sub y squared plus 1, is going to be replaced with 2. And my integral becomes the double integral over r of x squared plus y squared times the square root of 2 dy dx. Now I need to determine what r is going to be. So here's our original question. We said sigma represents the portion of that cone z, which is the square root of x squared plus y squared between z equals 1 and z equals 2. Well, if z equals 1, I get 1 equals the square root of x squared plus y squared. So I get x squared plus y squared equals 1. So a circle centered at the origin with radius 1. If 2 equals the square root of x squared plus y squared, I get x squared plus y squared equals 4. So I have a circle of radius 1 and I have a circle of radius 2 is my interest. Notice, visualize that cone all the way around. And if we look at the shadow in the xy plane, the shadow in the xy plane will be those two circles. And our region of interest is in between those two circles. That's what we're integrating over. So there is the projection of that portion of the cone into the xy plane. That is going to be my region of integration. So we're going to go ahead and convert this to polar coordinates where r is going to go from 1 to 2 and theta is going to go from 0 to 2 pi. That's what we're going to have here. So what does our total mass become? What's our integral going to be? What do we have? We have r goes from 1 to 2. We're going to have theta goes from 0 to 2 pi. X squared plus y squared is r squared. Then we have the square root of 2 here. And then dy dx, of course, is r dr d theta. Rewriting this, pulling the square root of 2 out and recognizing r squared times r is r cubed gets us here. And what is my inner integral? Inner integral, r goes from 1 to 2 of r cubed dr, antiderivative r to the 4th over 4, 2 to the 4th, 16 over 4, minus 1 over 4 gives me 15/4 for the inner integral, which brings us here. And of course, our antiderivative will be 15 over 4 theta, as theta goes from 0 to 2 pi, which equals 15 root 2 over 2 pi, which again gives us the mass of that portion of the cone from z equals 1 here up to z equals 2 here, as we go all the way around, given our density function z squared.